start. My name is Gideon Kaempfer, and together with me, Tali over here, will be presenting some work we did on scalability and high availability for Open Daylight. Specifically in the space of role management. We'll be discussing what we want to achieve here and what really role management is about in the context of our presentation. We'll talk about what's available today in the state-of-the-art of Open Daylight. There are mechanisms out there that can be used for that. And then we'll discuss, in the end, an implementation, which is actually a downstream implementation on Open Daylight, which was used in a previous version of our product, where we used an extension of the notion of what we call distributed functional role management. But the same ideas can be implemented inside the upstream Open Daylight. So I think it's as relevant as ever. So let's try to define what we want to achieve. Okay, and I'll try to do this through an example. So let's assume we want to implement something like a controller that defines for every subscriber on a wireless network, for instance, which path it needs to take in a network for service function chaining, for instance. It's just one example of many examples where we want to make decisions on a large space of IDs, if you like, or a large domain. In this case, the domain is the subscriber identities, which could be IP addresses, for instance. And for every IP address that we receive, for instance, from a AAA server on the top hand left, we want to make a decision through which instances of network functions to send that traffic through. So there's a lot of decision making to take place. These decisions may need to be made at very high speed. In this case, it could be 10 million subscribers with 10,000 decisions of what we call subscriber affinity. Decisions that need to be taken by the controller in order to configure OpenFlow switches accordingly. And if we want to build a highly available and scalable system, we don't want to rely on a single controller instance to do that work. So what we would like to do is to split the job, to split this role of deciding on, in this case, subscriber affinity into segments, and each have multiple instances of controllers, each be responsible for some segment of that problem. And in that way, we can create a situation where multiple controller instances can share the load. And at the same time, if a controller goes down, and maybe even more than one goes down, we can handle such failures by transferring the responsibility of the failed controllers to the remaining controllers. Okay, so what we're really striving to achieve is a situation where we can keep the load on the controllers balanced. Okay? We're not talking about network load balancing in this case, though the same kind of principles can apply to that domain, but we're talking about the load on the controllers for that matter. So what we really want to do is programmatically control the roles of the controllers, possibly in a large cluster. So maybe you're used to a single controller instance or a 3-controller cluster, but there is a possibility to have more than 3 controllers in a cluster. And in extreme cases, we're even talking about multiple clusters sharing responsibility for certain roles, which is also possible in a geographically distributed instance of certain problems. We're talking about large domains. So if there are 5 instances to be handled and there are 5 controllers, the problem isn't really interesting, right? So we can define that every controller would be responsible for a given instance, for instance, an OpenFlow switch. And if one controller fails and another controller can take over for that switch, the problem is not that complex. But when we're talking about a large domain, for instance, 10 million subscribers, then the problem becomes a little bit more complex, because when a single controller fails and there are just 5 controllers, then every one of them is responsible for 2 million subscribers. So now if we need to take care of which controller is responsible for every one of the subscribers, the problem becomes more interesting. And finally, we continuously want to preserve the load balancing between the controllers in every failure event. Okay, so we're talking about a system that needs to be highly available. It's not by chance that the example I gave you was from the domain of service providers. We're talking about a network that has to be very reliable. So we want to preserve the load balancing between the controllers in every instance in time, in every point in time. So let's talk a little bit about what's available in Open Daylight. Okay? And specifically, I'd like to talk about the Entity Ownership Service. Some of you may be familiar with the name. Who is familiar with EOS? Okay, quite a few. That's good. So you'll keep me honest. Not the expert on EOS. But what EOS allows is basically to define per ID, per entity, to define an owner. For instance, a controller that owns that identity, is responsible for that identity in some abstract sense. And in case that controller fails, EOS allows electing a new controller to be the new owner of that identity, where the new controller is elected from a group of candidates. So the terms used in EOS are an owner and a candidate. And you can have multiple candidates for a given instance. Okay, so that's the basic concept of EOS. Then you can get notifications regarding ownership. Don't really need to go into the small details of how EOS works, but you can understand this is a service provided as part of MDSAL. I should have said that. So you can actually get information regarding who is the owner of a certain entity, who was an owner of a certain entity, and things like that. And accordingly, you can act. And for entity ownership service, you can also define election strategies, meaning what happens if a certain owner fails. Okay? So you can just elect the next candidate on the list, or you can strive to get some kind of load balance decision. Okay? So maybe take a look at all the remaining controllers, see who owns more entities than the others, and select the least loaded controller, the controller with the least ownerships, to be the next candidate to be elected as the new owner of a certain entity. Sounds good. In essence, this could solve the problem if, for instance, in our subscriber domain that we described before, there wouldn't be too many subscribers. Or if we're talking about managing OpenFlow switches, as I mentioned before, it works perfectly. For instance, in the case of Network, every instance of the controller may be responsible for a certain subset of the OVS switches, or OpenFlow switches, on which the networks are controlled. But when we're talking about a very large domain, this becomes problematic, because basically what it means is that upon any controller failure, there may be a large number of entities that lose their owner. And that means that you get a burst of decision making every time that you have such a failure, and you need to elect new owners for every one of those entities. Just an example of a sequence diagram from EOS. You can register to listen on events of ownership for a given instance. You can request to become an owner of a certain instance. Typical things you would expect from this kind of management solution. And since I'm, as I mentioned, not a super expert on EOS, I think I'll suffice with that explanation. But I would like to point out things that I think are at least seemingly missing from the EOS solution. Okay, so does this service allow us to handle domains where there's a large entity of identities, a large number of entities? So as I presented so far, it seems no. But the real answer is that it's possible, but you need to use some kind of trick. The trick is that instead of handling ownership of singular entities within your domain. For instance, if you have 10 million subscribers, you don't want to handle ownership on a per subscriber basis. But if you unite subscribers into buckets, let's say of 1,000 subscribers, then or 10,000 subscribers, then your 10 million entity number becomes 1,000 entities. And at that point, maybe it's a more manageable number for MDCell to take care of in case of failure of a controller. So the first thing you want to do is separate your domain into buckets. A bucket would be, for instance, the hash function of a subscriber identity in my example before, maybe the least significant bits of an IP address to keep it simple. And in that way, combine multiple subscribers into a single bucket, and then from that point on, manage ownership on the basis of buckets. Of course, there is some downside to that, right? So because if now you take ownership on a bucket, you're assuming that a bucket implies load just like every other bucket. This could work if you have a good hash function, for instance, if you have a large number of subscribers mapped to buckets, and on average all the buckets imply the same load, but it's not necessarily the case. Also, you may still have a large number of buckets. So there are certain domains where they're so large that subdividing them into a few buckets can be problematic. And leaving the problem of redistributing the load to the point where you actually have the failure has some downside, right? So you're basically, what you're doing is you're making the decision at the point where the failure happens, while you actually could have made the decision in advance. So that well, of course it depends on the strategy, but if you have a fast failover mechanism, you're in a better situation, and you can then recover your next phase of handling a failure during the time that you assume you have between failures. Okay? In general, it also theoretically makes sense if you have, for instance, 1,000 buckets, right? And you have a small number of controllers, and you're handling reassignment of ownership on a bucket per bucket basis. You have, let's say, 3 controllers, 1,000 buckets. Every controller is responsible for 300 buckets. If a controller goes down, now you need to calculate new ownership for those 300 buckets that no longer have an owner. So basically what you're doing, and regardless of your reallocation strategy, you're implementing what we would call in theoretical computer science an online algorithm. So on a per bucket basis, you're making a decision on who the new ownership is, and you're not taking into account that you need to do this decision 300 times, right? So the first bucket, you're reassigning according to what you know regarding the load. The second bucket, you're doing that again. Theoretically speaking, it's not always the case in practice, but theoretically speaking, an offline algorithm can outperform an online algorithm, meaning if you would make a one-time decision for all the 300 buckets that need a new owner, you're theoretically in a better situation than making that decision bucket by bucket basis. Because in the worst case, I can give you a small proof of why an offline algorithm is better than an online algorithm. In the worst case, you'd mimic the online algorithm, right? So you know 300 buckets have failed, but you still decide to make the decision bucket by bucket. So basically, you're as good as an online algorithm. But maybe if you make the decision simultaneously for all 300 buckets that failed, you could be in a better situation, because you can, for instance, take a look at the final outcome of how you distribute this load. Maybe certain controllers have an advantage of managing certain entities over other controllers that are more closely related to other entities. For instance, if a controller has a responsibility for an OpenFlow switch, okay, and has maybe state in memory that relates to that OpenFlow switch, maybe that controller would be more appropriate to handle information regarding subscribers that are handled by that OpenFlow switch, right? So on a per subscriber basis or on a bucket per bucket basis, if I need to make a decision, probably the best I can do is take the least loaded controller and give it responsibility for that bucket of subscribers. But if I know that I'm going to have 300 buckets to deal with, maybe I can order those buckets in some way where I'll give 100 or 150 buckets to one of the two remaining controllers in such a way that each controller would get a segment of buckets that are more appropriate for that controller to handle. For instance, those buckets contain more subscribers that relate to the switches that that controller is responsible for. Okay, this is kind of an example where an offline algorithm will outperform an online algorithm for distributing load. And in our terms, defining roles. Yes.
So essentially, the way it's currently implemented is that we don't plan ahead for failures, because for each of those buckets, given the state of the cluster, you could actually pre-calculate who the backups for a particular bucket are, and then when a failure occurs, what you can do is immediately switch to the backup, which can be hotter than it currently is, and recalculate for the next failure, assuming no more than one failure occurs at a given point in time.
Right, exactly. So, well then, I'll call you up to the stage and you can continue the presentation. I think Tali will be happy, but but that's exactly the kind of thing that we're trying to achieve here. Basically, things that we've done. They're slightly different from the current concept of EOS. That's all I'm saying.
How are you dealing with like a flapping situation in case 2, right? You got a failure, you move over, recalculate, whoop, that came back up. And then you don't want to reallocate back, just have to go down again.
Oh, it's an excellent question. I mean, when you have flapping in any situation, there needs to be some kind of a quiescence period, as they call it, in which you don't make another decision. Maybe your controller went down and up, and maybe it's going to go down again, right? So typically in these types of algorithms, what you'll do is you'll make a reallocation decision under the assumption that you're currently in a static situation, and maybe you'll delay your decision until a point where there is quiescence, so where there are no longer frequent state changes between controllers. But of course, if there is a failure and you need to act quickly upon that failure, you need to load balance, at least remove the responsibility from a failed controller. If the controller comes back, the assumption is that you're building your system in such a way that you can actually handle one or maybe more failures. Okay, so you have to design your system in such a way that if, I don't know, you need 5 controllers in order to handle 10 million subscribers, then maybe you want to build a system with 7 controllers and be able to cope with 2 failures, and assume that if 2 failures occur and the 5 remaining controllers are sufficient to handle your load, even if they immediately recover, you may not transfer the responsibility back to them at that point in time. So you'll have a period of non-load balanced ownership, but you're correct that you would like to balance that back in order to be back in the original situation where you were ready for a failure.
There's also any quarantine, right? If you detect the flat and say this is quarantine, I'm no longer going to consider it a load balance.
Absolutely, absolutely. So there are a ton of theory about how to handle high availability events, and this is a classic situation. I mean, so let's see. I mean, the next slides will basically go into a little bit more of the details, just to give you another example of how to use EOS with buckets in order to do the load balancing. So just kind of go through them quickly. If, for instance, your address space is not IPs, maybe it's a MAC address, that the space that you want to divide, you hash that MAC to a certain bucket. So in this case, you would have n+1 buckets, each one mapped to a hash on a MAC address, and have, let's say, 3 controllers being responsible for every one of those buckets. And then in case of a failure of a controller, you would reallocate the responsibility to all the buckets of the failed buckets to the remaining controllers. Okay, that's basically the idea, but you still end up with the problems we described. I think I'll skip this part, though it's interesting because I want to leave some time for Tali to describe what we actually implemented and even in a distributed situation where we were talking about not just one controller but multiple controllers. I know you don't want this, but
So what I would like to describe is downstream implementation done by HPE. It is not based on entity ownership service, but it is based on Open Daylight clustering. So the main concept in this solution is an election table. It's quite similar to the entity ownership service with bucket mechanism, that each bucket has a primary owner and a backup owner. In this case, the owners are Open Daylight controllers, but our solution also enables ownership of other types of entities, like, for example, OVS switches. Why we want to do this? Sometimes we have large domain with thousands of OVS switches, and we have large number of subscriber flows. We don't want to install all the flows on all the OVS switches. So we would like to pick a primary switch and a backup switch and install flows only on those switches. If the primary switch goes down, we still have the backup. If the backup goes down, we can install flows on another backup. So this is more efficient and can scale better. So one of the controllers is selected to be the coordinator. The coordinator writes the election table into a distributed data store. This also allows multiple ODL clusters in different sites to synchronize on changes. The election table is propagated to all the controllers in the cluster in sort of three-phase commit algorithm. This is the classical three-phase commit. And this is our version of the three-phase commit. As you can see here, we have a multi-site cluster of Open Daylight controllers. One of the controllers, who is the leader of the cluster, has been chosen to be the coordinator of the election process. So it publishes to the distributed data store and a version of the election table. It contains a list of buckets with the primary and backup owners. Now each of the controllers reads its copy of the table and saves it locally. And when it's done reading, it acknowledges the distributed database. Only when the coordinator understands that all the cohorts have read the same version of the table, this table becomes operational and all the controllers start using it at once. Now we can see what happened in the case of controller failure. So controller number 3 fails. The immediate fast failover phase is that each of the other controllers marks ODL 3 as inactive in its own copy of the table. Now, if each of the controllers needs to access the owner of bucket number 2, it will understand it's ODL 4. The fast failover can last for a while, but we need to prepare for the next failure. So the coordinator calculates a new election table. This table has to have two requirements. One, it has to have minimum changes from the original table because some applications are very sensitive to ownership changes. And the other one is it can't include the ODL number 3 that failed, and also have to maintain load balancing. So in the same procedure like before, all the other controllers read the updated table, acknowledge that the new table has been written, and and now the new election table becomes operational.
What is this distributed PS? Is it every cell database or what is that?
In this implementation, no, it's not.
But it could be. In the implementation, it's a distributed database. Think of the sandbox. It could be every stuff for that.
I'm sorry, I'm kind of learning a bit more about the ODL. If leader dies, then what happens?
Then some of the other controllers become a leader, and
So then the
yeah.
leadership election,
Yes,
that has to take place first.
yes.
How does the in the world before the prefect does happen all the time in the ODS?
In this implementation, the heartbeats are done through the distributed database, but it can also rely on ACA heartbeats or other mechanism. So finally, a quick look about the implementation. So the coordinator has a state machine that reacts to high availability changes and publish new version of an election table each time high availability event happens. And the other side is the cohort state machine. Each cohort reacts to election table state changes and reads the new version. Questions? Yeah.
With the so each of the tables has a version, right?
Mm-hmm.
I assume this is a linear property, so essentially similar to election turning out, right? Would this information be visible to user applications? The reason why I'm asking is that essentially that correlates to a cluster term. And in OpenFlow, for example, if you're out for leadership, you supply a generation version, which is a 64-bit integer, which is increasing. So if I were to map OpenFlow onto this, then I would probably want to use the version of the table to in that message to the switches, so that I can efficiently isolate that failed node because it didn't participate, doesn't know about the new version. And then the OpenFlow switch can preempt any changes.
Yeah, currently we don't propagate it to the OpenFlow switch, but we do propagate to the other ODL so they can know if some ODL wakes up from a bad state and start sending acknowledgements on all the not up-to-date tables. We use this.
So the version is actually part of the table.
Yeah, it's part of the table.
Also, since there is an intermediate situation where you have a failure, but you're still on the older table, it really means that the table generation or version in itself is not doesn't necessarily mean that you know the state, the exact state of ownership, because in the intermediate state, you're kind of mixing owners.
Question? Thank you. Please visit us at the HQ.